Okay, so I'm Paolo Valente. I guess some of you already know me. This is a joint presentation with me, Linus, and Ulf. This is the agenda. So in the first part, I will talk to you about lag, in general, high latency problems in Linux, and these problems are inherited by Android because it runs Linux as a kernel. And I will show you a first step towards a solution to these lag, latency, frame drops, and all the rest problems. So this is the first part. In the second part, then Ulf and maybe also Linus, I don't know, will talk to you about recent developments with eMMC and blk-mq. So let's start from the, for my part. So let's talk about lag and, in general, high latency. So what's happening now? It's happening that these storage devices are fast and they are becoming faster and faster. So all problems solved, no more latency, so no more lag, no more frame drops in video playback, no gaps in audio playback, everybody's happy. Maybe. For example, a hot thread in Reddit last August had this title here. So why is Android lag build-up still a problem? It was a hot topic. So let's check. Let's see whether problems are solved or they are not solved. And let's do this directly with Android, with a common app, Facebook, using a high key. Basically, I will show you how long it takes to start Facebook. First, without any other I/O in progress, idle device, and then with some background I/O. For example, to mimic, I don't know, an app being updated. So, and this is the first part of a recorded demo made by Luca, if I, okay. Yeah, let's do this way. Okay, this one. Okay. So let me lower the volume unless you want to listen to the music. So this presentation, this demo is three parts, one about lag, one about video playback, and one about throughput. And this is the device and the software, with the configuration of the system, the hardware, which maybe you already know. So, where you can find everything. So first test, let's start Facebook. Ah, okay, it's reproducing there. Can you? Yeah. Anyway, it's a nice music. At least I like it. So let's start Facebook. I lost. Okay. This test is with No, but we would get the same results with any scheduler. Okay. If we start the app, it takes about 6 seconds. Okay. Let's do the same with some background workload. Let's start with only some reads. So 2 files being read in parallel. And this is only part of the workload that may be generated by, for example, an update. Writes are arriving in a moment. Again, same results with CFQ or deadline. I will talk about schedulers in a moment for those of you who don't know them. And this is what happens. Only 2 files being read. This is the lucky example that I'm showing you. Then I will show you the unlucky ones.
We've all seen that.
Yeah, I know. Okay, so this is what, just to show you this. If I become a friend of these slides again. I'm sorry, this is my first time with, maybe it's here? No. How do I restart the presentation? No, not with this one. I don't know. Okay, we can. I don't know, maybe you already see. Where? No. I really don't. Let's okay. Well, you can see it anyway. It's good enough. You can see. You can read. So lag is extremely high. They have not solved any problem. Is this only an Android problem? No. It's the same on a PC. And I will show it to you with a piece of another demo on a PC with an hard disk for video playback. I don't have time to show it to you also with SSD, but believe me, it's the same problem. Maybe I will tell you why the problem will remain also with higher speed devices. Okay, so I'm not going to show you only the problem, but also a solution, a possible solution. This solution is the BFQ I/O scheduler. So I don't know whether all of you knows what a scheduler is. In addition, I think most of you call them schedulers and not scheduler. Forgive me, but I'm accustomed to call it them schedulers. So maybe a few slides about this scheduler, so we are all on the same page. Oh, yeah, don't you hear me? Yeah.
Not for the video.
So these are block layer components. They decide the order in which requests are served. In particular, several processes are competing for the same device, so they act more or less like a traffic policeman who decides who passes on a crossroads. In this case, the crossroad is the resource, in particular the I/O device. What's their goal? Why do they choose a specific order? Well, to achieve these goals here: high throughput, low latency, high responsiveness, fairness, and so on. Where are these schedulers? Well, it depends on the, there are now two I/O stacks in the Linux kernel. One is the legacy block layer, and in that block layer you find the scheduler where I'm going to show you. Then there is another new I/O stack, and we'll talk about it later. So in the legacy block layer you have three schedulers: CFQ, Deadline, and Oneup. Basically, CFQ is the most accurate one. Deadline does something that I have not yet understood, and Oneup, as the name says, does nothing. So they decide the order by putting requests inside the request queue. From there, then they go to the driver. And note that in block there is only one request queue. This makes it basically impossible to keep the pace with fast, high parallel devices, and this is the reason why now there is a new stack too, which is block and queue. The main difference is that we don't have just one queue anymore, but there are multiple request queues. There is much more in block and queue. This is just a summary to give you just an idea. But there is a problem. No I/O scheduler yet in block and queue. And this is what we are working on right now, as I'm going to tell you. So what's the motivation for yet another I/O scheduler? Well, the motivation is that the other one are not very successful in achieving their goals. That is low latency, fairness, and all the rest. Instead, BFQ seems to work. So it really guarantees a high responsiveness, a low latency to software time application. So, for example, no more frame drops in video playback, a high throughput, and so on. So, but again, I prefer to show it to you at work instead of talking a lot about it, if I succeed in Okay, okay. Maybe we can do this. So, the same test, but this time with BFQ. Same exact workload, same device, same everything. And this is the result. We are about to lose 1 second. Okay, same background workload. This is only with, okay, again, if just to highlight differences, all the three side by side. Okay, this is only with reads, but the real problem are writes for a lot of reasons that I won't talk also about this now. And I'm about to show you what happens if we add just one write, just one. Okay. So this resembles a little bit more what happens if one app is being updated. If I can let's go. Okay, and we call this 2R1 write. You will see this. Okay, so the usual start with the idle device. Now with also one write in the background, and it's a problem for BFQ to 11 seconds. But the real problem is with no. It will never start. The application will never start. There is a problem also for BFQ because there are problems inside the virtual memory stack with writes, and these are completely out of control for BFQ. But they can be solved using BFQ, and this is something I want to work on.
There are also still problems in the eMMC device for the writes, which you cannot solve.
Yeah.
When you have ongoing writes, it will, by definition, have really long lag. And there's nothing you can do about that part.
Yeah. At least not the scheduler.
No, not the scheduler.
Not the scheduler, yeah. So there is a problem above virtual memory and a problem below. Yeah. We are in the middle. Okay. So the second part of the presentation is a video playback, but there is nothing because Luca has not yet finished it. Then I will show you the last part to talk with you about something else. Okay. Yes, since we don't yet have the part on video playback, I will show you what happens on a PC. Believe me, it's the same in Android on the high key, and we will show it to you in the demo Friday. Okay, but I can show it to you with a PC, also to prove, to show you that it's a problem also with a PC. Okay, so now I'm starting 10 files in parallel, 10 readers in parallel, and a movie. This is with BFQ, and you will see no glitch. Perfectly smooth playback. There are some problems with the playback, but this is because this video has been recorded while being played, but it's just a problem of the recording. We can also start a terminal, an application repeatedly during the playback. So we have 10 files being read in parallel, one application being started, and still the playback is perfect. Now you may say, okay, but this is because these scenes here are quite static, so they don't require a lot of bandwidth, but in a moment there will be a part with a change of scene. Also in this case, the audio was nice. And also with the more demanding part, no problem. Absolutely no problem. Okay, now the same with CFQ. So reset everything, CFQ, which is the best scheduler on an hard disk. 10 files. And now you are about to see that no frame will be dropped. Guess why? It doesn't start. The playback doesn't start at all. We could wait here, but we don't have time because we have started later. So the only way to let the video start is either you stop the workload or you switch to BFQ. I don't remember in this presentation, in this demo, what I did. Okay, stop the workload and then the video starts. Okay.
The question is, what's the exact reason for that video not starting now?
Yeah, this is the extra slide that, but I don't know if we have time. I would really like, of course, to answer your question. I don't know, maybe we can keep it pending and I can answer at the end, or tell me. I don't know. I don't want to steal time to your part.
We can do all stuff in
After.
You can go ahead and ask.
I think that's important.
Okay, so let me. Yeah. This is the answer. Use the throughput for the right requests. If you use the throughput of the device for the wrong request, then you will wait forever. The real problem is how do I guess which the right requests are? BFQ does that through some heuristics. As of now, in the last 5 years, they have worked for interactive applications and software time applications such as a video playback. I am continuously tuning them. They seem to work. So far, in any test I have done and through the user feedback, they seem to work. Okay? So CFQ is serving the wrong requests.
So it's on a brilliant idea. There might be other questions. Yeah, the time slot. No for tomorrow or today. Afternoon. So we have a time slot available today at 2 to half an hour in the
Near the card hacking session?
Yes. So we can be around there if people want to come and ask more detailed questions. It would be a good option.
Yeah, definitely.
Yeah.
Okay.
So do you know the room number? So it's next to the core dev hacking room.
It's session 2.
Session 2 at 2. We'll be there. Come and ask more questions about it if you're interested.
Meanwhile, I was trying to discover how to restart the presentation. But okay. Okay. So the last sub-part of my part, you can find all details on BFQ in its homepage. Everything, usage instructions, I don't know, papers that we wrote about it, results, patches, everything. And very short history. So BFQ was born in 2008 from a scientific paper that I wrote with Fabio Checconi. In the same year, Fabio implemented it, the very first version. From then, we have made a lot of enhancements, mainly me, but also other contributors. And now it's already available as a legacy. By legacy, I mean it's for block, BLK. It's not upstreamed, and you can also find it in various distributions. What's going on now? Okay, I have submitted it several times over the last 6 years, and has always been rejected for changing reasons, never related with performance or quality of the code or anything else, but other reasons. Meanwhile, blk-mq took over. Now block is considered legacy. So the last reason for reject was, okay, we cannot touch block anymore, so back off. Fortunately, there has been a sort of radical change for reasons that I don't want to discuss now. So all those obstacles have gone away, and the idea now is we want it, but in blk-mq. So this is what I am working on right now with Jens and other guys. Jens also offered to provide the framework that is needed to plug a scheduler like BFQ inside blk-mq. Okay, what's the present? I am collaborating with these maintainers and developers. Jens has already finished this framework and it's complete, it's working. And 2 days ago, I have finally submitted the first patch series for merging. So we are aiming for 4.12. Everything seems to go on smoothly. I'm crossing my fingers. And that's all. So if you want to see more on BFQ-mq, come on Friday, because we will try to show something. How is BFQ doing in blk-mq? We will also show on the same table BFQ at work on the high key, in particular the part that I couldn't show you now for the video playback, but in general I will show you throughput, responsiveness, latency, and so on. So this is about blk-mq. What about Android? Linaro is basically supporting the BFQ-mq project, and this is a little bit far with respect to Android because of the older kernel versions used in Android. But results with Android, for me, are very exciting. This is exactly what I showed you. Lag is a problem. The work to do for Android is not trivial because the first part is a backport, okay, to 4.4 or 4.9, but this is not sufficient because as I showed you, BFQ has problems too when there are writes because of the virtual memory, and these problems are nastier in Android for several reasons. So there is much work to do to solve also that other part. I already have a prototype that solves the problem inside the virtual memory, but it's only a prototype. There is a lot of work to do to have it working really on a real system. So I'm trying to push also in this exact moment to get support also for this part, which I think is very interesting. So I'm pushing with Linaro and trying also with Google. I don't see it out now. Okay. So the future. There will be the same problems also with next generation devices, maybe even worse because they have multiple queues and deeper queues, and to achieve a high throughput, you must keep these queues constantly filled with enough requests, and this is not easy at all. If you keep these queues filled, then you lose completely control on the order in which requests are served. So it's a really, really hard problem to solve. Okay? If you want throughput, you lose control. If you want control, you lose throughput. With these devices, BFQ has limitations, basically because we have divided it for block and older, slower devices, so it has a higher overhead than a minimal scheduler, and I want to show it to you quickly. It's about 50 seconds, I guess, again with the demo. So, these 4 workloads here, the 3 readers, sequential and random, and the 2 readers and the writers, sequential and random. The comparison against NOP, because it's the best performing one. So with sequential reads, as you can see, the throughput is the same. Okay. Yeah, we started 10 minutes later. And with writes, you have a much higher throughput because NOP privileges writes and writes are slower. But with random I/O, the throughput is lower because there are many more IOPS. BFQ has a higher overhead for each I/O, and in this case, the CPU is made of many slow cores. So one core gets saturated, and we are working on that too to solve this overhead problem. And I think this is all. Let me see. Yes, that's all. That's all for BFQ.
which slide on this thing?
Good luck.
I will do it manually.
Okay.
All right. So this was, yeah, that's my slide. To be able to use BFQ with the eMMC devices, which are single hardware queue, you have to refactor eMMC to support MQ or MQ and the old block layer. We are still talking about that. Different block layer maintainers have different opinions on whether you should support the legacy block layer as well, or just make a clean switch over like UBIFS did, for example. I have done a patch series that converts eMMC SD to use MQ. It's not giving any bigger performance regressions. A little bit, because you have to switch things over to do cache flushing and so in a different way. We can discuss the details if you're interested. But there exists such a patch set for demo purposes. It's 32 patches in total. I have merged half of them, but they are preparatory work. And I'm currently discussing mainly with Adrian Hunter from Intel, because he's working with this command queuing, which is another feature that is speculative pipelining of writes and reads to the eMMC card. You have only one hardware queue, but it's deeper. And when you fail something in this hardware queue, or this software hardware queue, you have to back off everything you did up to until that point. So it's not like you can issue things in parallel and expect the other things to be completed. You have to back out. And this is also being pushed by the eMMC SD card vendors and JEDEC at the same time as we're working with this. We think that the multi-queue block layer will be a better fit, because it has a more intuitive way and the nicer data structures, and it has a future. That's also a good thing. So that is happening, and yeah, that's it. Are we out of time? We are. All right, thank you.
So just to repeat one thing, don't forget about if you want to have more questions, come and see us at 2 this afternoon. Thank you.